In previous videos, we've discussed how to use Kirchhoff's rules to get equations to describe a circuit that we can't reduce. In this video, I want to approach and show you how you can use linear algebra to quickly and simply get a solution to a set of linear equations like the kinds of equations you get from Kirchhoff's rules. Now, the intention of this video is not to teach you the principles of linear algebra. That is way too big a topic. And honestly, it's better done by other people in other videos. In fact, I would recommend if you're taking linear algebra or if you have already taken linear algebra, I would definitely recommend the series of videos called Concepts of Linear Algebra by the channel 3 Blue 1 Brown here on YouTube. They go through and describe very well some of the geometric interpretations of the kinds of principles that you proved in linear algebra. The purpose video instead is to show how the equations we got using Kirchhoff's rules can be solved very rapidly if you can use and apply the principles of linear algebra. Here you can see the equations we got when we applied Kirchhoff's junction rule and Kirchhoff's loop rule to the top and the bottom loop in our circuit. If you don't know how we got these equations, I recommend you go back and view my video on applying Kirchhoff's rules and the example problem I went through. Now, the idea of how to use linear algebra to solve a system like this is ultimately we're trying to find a matrix, a way to write these equations in this sort of matrix form where I have an A matrix multiplying a vector that contains my variables I1, I2, and I3. And that matrix times that vector will equal some other vector that contains the results. Now, the reason why I want that is because I can take that form and turn it into a non-square matrix. Now, this would be a non-square matrix where I combine the matrices A and with my vector B. And from there, I can get this matrix in what is known as reduced row echelon form. And if you're not familiar with what that is, then you haven't studied linear algebra, because honestly, that's a huge part of linear algebra, is learning how to take a matrix and get it into reduced row echelon form. There's other principles you'll learn as well, but this is such a huge part of the calculations you do in linear algebra that honestly, this is the use for, one of the uses for finding reduced row echelon form of a matrix like this, a non-square matrix. So why do we want to do that? Well, if we can get this into reduced row echelon form, this non-square matrix into this reduced row echelon form, our A matrix is just going to be ones along the trace. And what's left over on this in this B matrix is going to be the answers to our problem, where whatever is left here, the number on this in this position, that is going to be my I1 current. Whatever is left in this second position on the end is going to be my I2 current, and whatever is left in this third position is going to be my I3 current. So that's kind of the method. We're going to take our equations and we need to arrange them so we have an A multiplying our equations, and on the other side of our equals sign is then our B vector, so that we can combine it into this non-square matrix. So the first thing we're going to need to do is take our equations as we've written them and rearrange them. So we're going to have some stuff multiplying I1 and some other stuff multiplying I2 and some other stuff multiplying I3. And then everything else, every term that is not multiplying I1, I2, or I3 is over here on the other side of our equation. If we do that, we're going to get something that looks like this. You'll notice this. Now I have my equations, and I've just rearranged my terms so that I've got every equation has something multiplying I1, something multiplying I2, and something multiplying I3. And everything that isn't multiplying I1, I2, or I3 is over here on the other side of my equation. You may have to insert zeros because some of our equations, like this middle equation, doesn't have I2 in it. Well, that just means that it actually does, but we've got 0 multiplying I2. You'll also have to be careful because any of our terms not multiplying I1, I2, or I3 have to be moved over to the other side of the equation. So you want to be careful of your minus signs. But now we've got this, our equations rewritten so that we have it in sort of this A and B form. And we can take that now and write our AB matrix. We're just going to have all of our coefficients. We leave off the I1s, I2s, and I3s, because really that's going to be understood. And if you understand how matrix multiplication works, how to multiply a matrix by a vector, then you can see that if I perform this matrix times this vector, I get back to my earlier equations. Now at this point, you could solve it algebraically, and honestly, if you have a calculator or a computer that will do the reduced row echelon form reduction of this algebraic matrix, then more power to you. But it would be useful probably to, at this point, insert our values. So remember our values for epsilon 1, epsilon 2, R1, R2, and R3. We just plug those into our matrix. And so we now have this new matrix with our values included. What have we gained? Honestly, we haven't gained anything other than we can leverage the power, the ideas of linear algebra. But it seems like so far we're trading one complicated algebra problem for another. Here's the real power. Almost every calculator, a graphing calculator that I know of, has somewhere buried in it a function for taking a matrix and getting it in reduced row echelon form. And that's the power. If I can get it into this matrix form, then I can enter the matrix into my calculator, hit reduced row echelon form, and bam, I've got my answer. To recap, we took the equations we got from Kirchhoff's rules and we arranged them so that we could insert them into a matrix. From there, we can put that into our calculator, and by using this reduced row echelon form and just function, we can get our calculator to tell us what the answer is without having to do a bunch of complicated algebra. And you'll see, like I said, there's ones on the trace of that A matrix, and then the results from the B vector are our answers. And so our answers are for the current through R1 and through the battery here, this top branch, that is 0.02 amps. The current through the middle is then 0.02 amps. And so we have this flow of 0.02 amps here in this sort of loop. And in this bottom loop, we have no current. So this is just an easier way to get the answer to these kinds of linear equations. Now, if our equations are not linear, for example, if instead of finding the current I1, I2, I3, we wanted to find I1, I2, and maybe R3. Well, if that's the case, then we might actually still be okay, because we have a current going through here, we have a current going through here, and we'd have to know what I3 was. But if we did that, then we could get R3. It would just be, instead of having a vector where this is I1, I2, and I3, we would instead maybe have a vector where it's I1, I2, and R3. However, if we'll get nonlinear equations if we're trying to find, say, I2 and R2 together. I think you can still solve that situation using Kirchhoff's rules, but you might not be able to use linear algebra to do it. You might have to go through the full substitution method and the other techniques for solving systems of equations because your equations are technically not linear. So that's just one thing to watch out for. But honestly, that's a very rare case. And in general, and especially in an introductory course like this, you're going to have a set of linear equations that we can turn into a matrix and use the tools of linear algebra to get our answers. And that just is really slick. So I wanted to show you that, especially since this is the kind of thing that you don't get to see in a regular linear algebra class. However, if you don't know what in the world I just went through, if you don't understand linear algebra and you're not familiar with the techniques of linear algebra or reduced row echelon form, then don't stress about it. Use the regular techniques that you know, and you can still get the answer to a problem like this. Okay, so if you have any questions, come see me in my office or come talk to me in class.